Welcome, everyone. Today, we're setting the stage for an absolutely epic, continuous journey back in time. We're going to witness the ultimate origin story in this explainer. We're not just, looking at old rocks and gas here. We're exploring the incredibly dramatic, violent, and honestly beautiful evolution of our very own solar system. We're going to watch it completely transform from a chaotic, swirling cloud of dead stars right into the perfectly tuned planetary neighborhood that we call home. We'll be guiding you through the literal construction of our world step by cinematic step.
Take a look at this quote and just let it really sink in for a second. Every mountain, every ocean, every person began as cosmic dust. I mean, it sounds like poetry, right? But it's a literal, undeniable scientific fact. The iron in your blood, the calcium in your bones, the water in your cup, literally none of it was created here on Earth. It was all forged in the cosmic dark billions of years before our planet even existed. So today, we're tracing the exact lineage of that stellar dust.
Now, to really understand our beginning, we kind of have to rapidly zoom out and look at the macro history of the universe. So, 13.8 billion years ago, the Big Bang sparks existence, giving us all that hydrogen and helium. Then, around 13 billion years ago, coming out of the Dark Ages, the very first stars ignited. Galaxies started assembling, and by 11 billion years ago, our Milky Way galaxy had taken shape. But our story doesn't actually start there. We have to fast forward through entire generations of massive stars just living and dying until we finally reach our specific starting line, exactly 4.6 billion years ago.
Okay, let's dive into this with Chapter 1, the ancient cosmic cloud. Picture this. Before there was light, before there was a single planet, there was really just this, a vast, dark, freezing expanse. We're basically looking at a giant molecular cloud, which is this massive stellar nursery made entirely of hydrogen, helium, and swirling cosmic dust. But here's the crucial part. It wasn't empty. It was seeded with heavy elements. Studies of ancient meteorites actually showed traces of isotopes like iron-60, which, by the way, can only be forged in the extreme heat of exploding massive stars. That means our primordial cloud was effectively a cosmic graveyard, deeply enriched by the radioactive debris of ancient supernovae that lived and died long, long before our sun.
For millennia, this cloud just drifted. It was totally stable, completely dormant. But then, an explosive catalyst changed absolutely everything. A neighboring massive star reached the end of its life and just detonated in a brilliant supernova. Imagine this colossal, cinematic shockwave ripping through the vacuum of space, slamming directly into our dormant molecular cloud. This incredibly violent impact compressed all that gas and dust, creating these super dense pockets. And, pushed past the tipping point, these regions literally could no longer resist their own mass, and they began violently collapsing inward under the crushing force of their own gravity.
Which brings us to Chapter 2, Gravity and the Spin.
So as this massive cloud shrinks, what physically happens when something on this astronomical scale rapidly collapses inward? Well, it doesn't just shrink perfectly into some static little sphere. To understand this new dynamic, we need to look at angular momentum. Think of a spinning ice skater. When a skater starts spinning with their arms outstretched, they move at a certain speed, right? But the moment they pull those arms in tight, they suddenly spin much, much faster. That's the conservation of angular momentum at work. And because our giant molecular cloud had this slight initial rotation, gravity forcing all that material inward caused the entire nebula to spin faster and faster.
Now you've got these competing forces. Gravity is pulling inward, gas pressure is pushing outward, and there's this extreme centrifugal force. Together, they warp the cloud completely. Over about 100,000 years, this chaotic, spherical cloud flattens out into a highly organized protoplanetary disk. I want you to imagine a colossal cosmic pancake, spanning a massive 200 astronomical units wide. For context, that is 200 times the distance from the Earth to the Sun, just swirling relentlessly in the primordial dark.
Moving right along to Chapter 3, Ignition of the Sun.
While that massive disk is out there swirling, let's pull our attention away from the edges and look right into the hyperdense center, because that is where the true power of the solar system is being forged. Look at this staggering number right here, 99.8%. As the disk spun, gravity basically acted like this unrelenting vacuum. It gorged itself, drawing in gas and dust until that central core held 99.8% of all the mass in the entire solar system. I mean, let that sink in for a second. Jupiter might have a big ego, but everything else, every single planet, moon, and asteroid, is made from a literal cosmic rounding error. Just that leftover 0.2%. So,
the temperature and pressure inside this massive core became completely unimaginable, first forming a hot, super-dense T-Tauri protostar. But within about 50 million years, the pressure finally crossed a critical threshold. Deep within the core, hydrogen atoms were literally crushed together so hard they formed helium, which triggers nuclear fusion. In this blinding, totally cinematic flash of energy, hydrostatic equilibrium was finally achieved, meaning the outward pressure of fusion perfectly balanced out the inward crush of gravity. And just like that, our main sequence sun was born, flooding the dark solar system with its very first light.
And that sparks Chapter 4, Worlds Under Construction.
Okay, so with the sun now roaring with nuclear fire, we're going to shift our focus back to that remaining 0.2% of material. You know, the cosmic leftovers swirling around the newborn star. They're finally ready to build some worlds. The core mechanic driving this is called accretion. It's essentially a violent cosmic snowball effect operating over millions and millions of years. The particles in the disk didn't just passively orbit, they were violently interacting.
Try to imagine watching this happen like a fast-forward time-lapse film. First, microscopic dust grains, driven by static, electricity, and just really gentle collisions, start sticking together. Then, these clumps grow into pebbles, and then into boulders. As they get bigger, their gravity increases, right? So they pull in even more material, smashing together to form these jagged, 10-kilometer-wide planetesimals. From there, it is just a relentless demolition derby. Planetesimals crash into one another, they merge, they melt, and eventually they form massive, spherical protoplanets. You are literally watching worlds being built from scratch right out of dead stellar dust.
Now let's explore Chapter 5, the Frostline Divide.
Now, you might be wondering, why exactly do we have small, dense, rocky planets close to the sun, but these massive, sprawling gas giants way further out? Well, the answer actually lies in this crucial invisible boundary in the early solar nebula called the frost line. Located roughly between the modern orbits of Mars and Jupiter, this was the absolute dividing line between the scorching heat of the inner solar system and the freezing depths of the outer solar system. And this temperature threshold, it completely dictated a planet's ultimate destiny.
Let's contrast these two zones for a second. In the inner solar system, it was just way too hot for things like water or methane to remain solid. Only compounds with really high melting points, we're talking rare metals and rocky silicates, could actually survive. And because these materials were relatively scarce, they could only form small terrestrial planets. But if you look beyond the frost line, it was absolutely freezing. Volatile compounds froze solid into highly abundant ice. With so much more solid material available out there, the outer planetesimals grew into colossal cores. These massive cores became gravitationally powerful enough to just suck up the abundant hydrogen and helium gas directly from the nebula, ballooning into the giant planets we know today, like Jupiter and Saturn.
Which naturally leads us to Chapter 6, the cosmic leftovers.
Of course, the massive planets didn't consume absolutely everything. Let's take a slow outward pan through the rest of the solar system. Right between Mars and Jupiter, we have the asteroid belt. Millions of rocky remnants that Jupiter's massive gravity aggressively prevented from ever forming into a planet. Then, moving way past Neptune, roughly 30 to 55 astronomical units away, we hit the Kuiper belt, which is this really thick ring of icy bodies and dwarf planets. And finally, stretching incredibly far out, up to 100,000 astronomical units away, lies the Oort cloud, a vast, spherical shell containing billions and billions of comets. Honestly, these regions are like ancient, untouched time capsules.
But you know, these belts weren't always exactly where they are today. Early on, planetary migration, dictated by something called the Nice model, saw the giant planets engaged in this incredibly complex gravitational dance. Jupiter and Saturn actually fell into a resonance, creating this massive gravitational push that sent Uranus and Neptune surging outward. Neptune plowed violently into the ancient Kuiper belt, which initiated a billions of years-long demolition derby. This aggressive migration scattered icy bodies everywhere, literally throwing some inward to deliver precious water to our rocky planets, and flinging others way outward to populate the distant Oort cloud.
And guys, that brings us right back home. Amidst all this extreme violence, massive planets migrating, asteroids just smashing together, comets raining down, and giant impactors destroying early worlds, how on Earth did one specific inner protoplanet survive? How did the Earth not only survive this chaotic cosmic demolition derby, but somehow manage to cool down, gather liquid oceans, and actually harbor life? From a dark, swirling molecular cloud seeded by dead stars, a perfectly ordered gravitational system emerged.
The grand mechanics of angular momentum, extreme gravity, and violent accretion sculpted a solar system containing a tiny pale blue dot, a dot destined to eventually evolve conscious life capable of understanding its own history. Studying this history isn't just astronomy, folks, it's exploring our profound shared origin story. We are literally the universe, observing itself. But amidst the chaos, the planetary migrations, and the cosmic demolition derbies, what exact miraculous sequence of events allowed this specific pale blue dot to wake up? Keep wondering, keep looking up, and we'll explore that mystery in our next explainer.